is all about using the derivative rules to answer questions. And we're starting with 3.1, which is we're going to use the derivative to find extrema on an interval. So let's kind of look at the title first. Extrema, you may have not heard that word like that specifically outside of a math class. Does anyone know what extrema is? Yeah, maximum, minimum values. Extrema is basically plural, and you can interchange it with extreme values, plural, okay, plural. So extrema means extreme values, but when we say extreme values on a graph, are we talking about x values or y values? Y values, yeah. So extrema are going to be extreme y values. That they're interchangeable. Extrema, of course, is just a little bit more concise. There are two types of extreme y values that we're going to be looking at. And you can categorize them two different ways, believe it or not. You're going to have maximum y values, which you can abbreviate max, and you're going to have minimum y values, which you can abbreviate min. High values and low values, essentially. But each of those can be classified two different ways. You can have what we call local or relative, max or mins, for either one of them, I guess. We'll do it like this, local or relative mins, local or relative max. But then the other versions are going to be global / absolute. So you could subdivide those as well. And you could have also said that they started with global or local and then max mins. Now, if you're using the terminology, local and global are kind of nice because they kind of have that geography feel to it, right? Local means within a certain vicinity, and global means not being ethnocentric, right? Thinking beyond your local vicinity. So we use those two terms in conjunction with each other, but sometimes we'll talk about relative max versus an absolute max, and they mean the exact same thing. Relative means on a relatively small interval, and absolute means absolutely everywhere, right? So I'll use them interchangeably. College Board will use them interchangeably. We'll get used to them. So we need to kind of talk about then not just what these are, but how do they relate to calculus and how can we find them without a calculator. All right, so let's go ahead and define the first type we're going to look at. We're going to look at the absolute extreme values and the global extreme values. Now, the way it's written here, notice the qualifiers, the adjectives. The slash means what? When you see absolute / global, what does that mean kind of contextually? That they're the same, that these two terms are interchangeable. They mean the same thing. Whether you're calling it absolute max or a global max, it doesn't matter. But what does something usually mean when it's written in parentheses like that, when a qualifier is written in parentheses? Like find the value or values. It means that it can be omitted, believe it or not. So that's kind of important to start with. If you just talk about a maximum y value and you don't say global and you don't say absolute, if you just say a maximum y value, guess what everyone who's in the know is going to assume you're talking about? You're going to be talking about the absolute max or the global max. So you don't need the qualifier there when you're talking about an absolute max or a global max. You can just say max. What does that mean then when you're talking about the other type, when you're talking about a local or a relative? It's important to have that qualifying word in front of there. And we'll emphasize that as we go through and find these things. Okay, so let's define an absolute max or min, or a global max or min, or just a max or min. If f of x or f is some function on some interval, and it could be an open interval, it could be a closed interval, it could be half open, half closed, then y equals f of c is, number one, the absolute maximum y value, or the global maximum value, or just the maximum value on that interval. The IFF means if and only if. If and only if, which means it's bidirectional. And this is an important way to define it. If and only if that y value, f of c, is greater than or equal to all the other y values f of x on the interval. That's how you would read that. So f of c is going to be called the maximum y value on the interval if and only if that y value is greater than or equal to all the other y values. Does that make sense? Yeah, now another way to read that is he's going to be the absolute maximum y value if there are no other y values greater than it. That's another way to say greater than or equal to. And very similarly here, f of c is a y value that's a minimum if and only if it is less than or equal to all the other f of x values, all the other y values on the interval, less than or equal to. So now there's no other y value that is lower than it on an interval. Now the equal sign is kind of nice because it says that there could be other y values that are the same value, yes? But because they're the same, it's going to be just one maximum value. There can only be one absolute max. There can only be one absolute min, right? Only one, if it exists. All right. It says note here, we cannot say that the maximum value is necessarily the biggest one on the interval. It's not necessarily the biggest one on the interval, but rather there are no other y values bigger than it on the interval. You'll see what I mean. Example 1, the graph of g of x is given below. Determine the extrema. Again, what does extrema mean? Maxes or mins. Absolute, global, or relative local? If I don't say what type of extrema, I just say extrema, you're assuming what? The global, the absolute. And these are y values or x values? Extrema. They're y values. That's very important. On the interval, on the closed interval from A to F. On the closed interval from A to F. Okay. Well, that's easy. If we're including the endpoints, you could put solid dots there, solid dots there. Is there a y value on the closed interval such that there is no other y value lower than it? Yeah. At what value of x do we have the absolute minimum? A, right? If you draw a line straight across. That other one over there comes kind of close, but it doesn't. So we have an absolute min, or you could say a global min, or you could just say a min. Now let's put something in front of there. How about g of x has an absolute min, a global min, or a min of what? If the function's name is g, how do we talk about the function value at a? G of a. Yeah. At x equals a. So here's kind of the typical way we describe it. The function g of x has an absolute minimum of the y value at x equals. So when you say of, you're talking about the actual value. When you say at, you're talking about the x value. So the x value becomes the location of the absolute min. Do we have an absolute maximum? Yes. At what value of x? D. So now we could say G, and here's another way to write it. G has a max of G of D at x equals D. That would probably be the most concise way to write it. You don't have to say G of x. The function's name is G. It has a max. Of course, that's the shortest way to write global maximum, because you don't have to put absolute or global, and then you can abbreviate maximum max of G of D at x equals D. There is no y value bigger than it. Perfect. That was not difficult at all, right? When you have the graph, all you have to do is just look at it, yeah? Okay, any questions on that? Nice way to start. Does that even require calculus? No, not much. But we're practicing our notation as well. All right, example 2. Sketch the following functions on the given interval and then determine the extrema if they exist. Oh, it was so nice to have the graph given up here because you could just look at it, right? Down here we're not given the graph, but the instructions say to go ahead and sketch the graph first so we could just look at it. That makes sense. Success is built right into the instructions there. Okay, so notice we have a closed interval. We're looking at a piece of this parabola from -1 to 2. We don't need a calculator to sketch that squared plus 1, right? That's just our, I'm happy to be in a math class, smiling parabola that is shifted what? 1 unit. up. So I'm just going to call that 1. And here we go. Should have y-axis symmetry still. So I'll try and draw it the best I can with my Art 1 skills. It was a high A in Art 1, but it wasn't 100. And it was years ago. It looks good enough. Now, the interval is kind of important. We're looking from -1 to 2. So I think I am going to highlight, or at least trace over in a different color, the piece of the function that I'm interested in. I don't want to be lured or distracted by other parts of this graph that aren't in the interval that's being specified. Okay, now I think it's pretty obvious, right? This function is going to have, let's do the max first. F has a max, and when I say max one more time, what time do I mean? Global max, absolute max, of what? F of 2, right? Now, we could do better than F of 2 in this case because we have the equation. So let's try and be a little bit more detailed. F of 2 is the same as what? Y value? 5. You can plug it in at x equals 2. So that happened at the right endpoint. It's good to know. If you recall up here, the local min occurred at the left endpoint, but the maximum occurred on the interior. That's interesting. Okay. Do we have a minimum value? Yes. F has a minimum of what? 1. Yeah. You could say F of 0 equals 1, or you could just say a minimum of 1. That's fine. If you just say a minimum of 1, we know it's what type of number, x or y. The y value. And it occurs at x equals 0. And that one's going to be on the interior. Sweet. So we're already kind of establishing some insights here as to the possible locations, x locations, where these absolute extrema can exist, right? Apparently, they can exist at endpoints. Would you agree? Yeah, here we had the max at the right endpoint. Up here we had the min at the left endpoint. But they could also occur on the interior, but not at any point on the interior, right? What's significant about that point on the interior as it relates to, I don't know, calculus? Yeah, the derivative equals 0 there. Yeah, f prime equals 0 there. And similarly up here, the absolute maximum occurred on the interior where, again, the derivative was equal to 0. Not of x, I should say it was d. So that's kind of interesting. It's kind of interesting. Did this point right here, this y value, did he have a shot at being an absolute max or min? No, because there were points to the left that were lower. Sorry, you can't be the min. And there were points to the right that were higher. Sorry, you can't be the max. You can still be a somebody. You just can't be the absolute max or absolute min. There's a role for you. Okay, pretty nice. Let's look at the next one. It's x squared plus 1, but notice what's different about it. We're on the open interval. Hello. Thank you. Mr. Clark, at 11:30. You have a date. All right, so let's kind of use technology to our advantage. Let's go ahead and just copy this graph here, and we'll slide it over here. And now the only difference is I'm using open intervals. So if you want to, let's see, switch to white, a small white one, you can now come over here and color in white. That's kind of neat. And now you kind of have the interval that you're looking at, right? We can even do better than that. We could label this left endpoint -1. If you plug it into x squared plus 1, you get 2. And up here, you plug in your 2. Of course, we got 5. And the y-intercept was at 1. So we can look at that. Might be a little bit more useful just for graphing purposes. Okay, let's go ahead and do the same analysis. We're looking for max or mins, absolute max or mins. Do we have any? Do we still have a max? No, there's no max now. Why? As x gets infinitely close to 2 from the left, our y values are getting infinitely close to what? 5. Do we ever get to 5? No. So if there were to be an absolute maximum value, and this is not a limit anymore, we're not talking about a limit, we're talking about an actual y value that we can claim stands right there such that no other y value is bigger than it. And you could say that it's 4.999999999, but when you run out of breath and you're going to stop saying nines, guess what? I'm going to add another 9 to the end and go, see? And now I'm closer to 5 than you are. So it would be the very first real number less than 5, which is what, Garrett? Do you know the answer? The first.
Could you define a max by a limit?
No. And that's what I was trying to emphasize. A maximum value is an actual y value, f of c, where you're standing there and you're saying, I am the max because as I look everywhere else on the interval, I see no other y value taller than me, or taller than I am, is the correct way. Okay? So you can't define a maximum as a limit. I mean, that's why we have a limit. It would be correct to say the limit as x approaches 2 from the left-hand side of f equals 5. Okay? But we're not going to say that the maximum value is 5. All right, so there's no maximum there. Is there a minimum, though? Yes, we have a minimum. F of x has a minimum of 1 at x equals 0. Okay, so in part A, we had both a max and a min. One of them occurred at an endpoint, and one of them occurred where the derivative was 0. Nice to know. On part B, we didn't have a max, but we still had a min, and it occurred where the derivative was 0. What was the difference so far from A to B, where we had both the max and the min, but over here just one of the two? The thing that kept me out of the max was the fact that the right endpoint was open. Interesting. Letter C, what the? Oh, okay. It's going to be x squared plus 1 everywhere except at 0. And then at 0, we're explicitly defining it to be 2. I could do that. In fact, I could just take this graph, copy it, paste it over here, and all I have to do now is get my little white tool here and come over here at x equals 0 and take away the y-intercept. Right, take away the y-intercept at 1 and explicitly call it what? 2, which is right here. Okay, sweet. Oh, the endpoints are now filled in as well. Yeah, I didn't even look at that, but we're back on a closed interval. So I can actually fill those back in. That's nice. And maybe I'll accent that a little bit more. There we go. So it's open. Thank you. Okay, so now there's a nice graph that we just kind of modified. Does F have a max? Yeah. So F now has a max of 5 at x equals 2. And again, notice we're back to a closed interval, at least at the right endpoint where the max occurred, so that's good. Do we have a min now? There's no min. And again, it's for the same reason as the previous where there was no max. We took the old y value away that was at the vertex, at the bottom there, and we took it away. So now from both sides, you can get infinitely close to y equals 1, but you don't ever get to a definitive y value that can say there is nothing lower than I am. So there is no min. So what was the difference? Well, we had a closed interval over here, and we had both a max and a min. But we have a closed interval over here, and we don't have a max and a min. So if we're interested in determining not only the values of x where the max and mins can occur, but under what conditions are we guaranteed to have both a max and a min, it would look like having a closed interval is part of it, right? Because as I saw over here, if I don't have a closed interval, I'm taking away an endpoint, which could possibly be a max or a min, right? But it's more than just having a closed interval, because as I saw here, which was a closed interval, I didn't have a min. So what was the difference between this closed interval, where I didn't have them in, and on part A, where it was a closed interval and I did? What's the difference? It was continuous on the interval, which means, it would be differentiable and therefore continuous. Yeah. But I think continuity is really what I need. I don't really need it to be differentiable as long as it's continuous, right? Because there could be like a sharp turn. And would this still be a local minimum? Yeah, so it has something to do with the fact that this function was continuous at 0, and this function was not continuous at 0. So it has something to do with closed intervals and continuity. Interesting. All right, let's shift functions now and explore something else. Sine of x on the closed interval from 0 to 4. Well, it's a closed interval, right? And sine of x, what do you know about sine of x being continuous? Everywhere. So now I have a function that is continuous on the closed interval, much like I had up here on part A, where I had both a max and a min. Do you anticipate having both a max and a min on part D? Possibly. I like that. Possibly. I'm going to go out on a limb and say maybe. How many cycles do we see from 0 to 4 pi? 2. So I'm going to call that 4 pi. Here's 2 pi. Half of that's pi, and then I have pi halves. Now I have my quarter cycle counting interval, so 3 pi halves. And then I've got half of that is 3 pi. So I got 3 pi halves, 4 pi halves. That's going to be 5 pi halves, 6 pi halves, 7 pi halves. So remember doing that in pre-cal? The amplitude is what? The number in front's 1, so we're going to go all the way up to 1 and down to -1. Now sine, we graphed by saying not chala, but sahala. So it starts on an axis. So we go axis, high, axis, low, axis, high, axis, low, axis. And again, every time we go to another critical value here, we count by another pi halves. Okay, so now with the graph and everything labeled, notice that was kind of nice. We can quickly answer the question. The function's name is f. F has a, does it have a max? What is the maximum value? You said it has 2 of them? Good. It has a maximum value of 1. Again, there can only be, if there is any, 1 maximum value. That's why we call it an absolute max. There can't be 2 absolute maximum values, but they can occur at more than one place. So we have an absolute maximum value of 1, and it occurs at x equals pi halves and 5 pi halves. Make sense? 1 absolute maximum value, but it occurs at more than one place. Do we have a minimum value? Yes, f has a min of what? -1, and it occurs also at 2 places, at x equals 3 pi halves and 7 pi halves. So just like it was above on part A, we had a function that was continuous on a closed interval, and we had both a max and a min. And up above on the parts B and C, where we had functions that either were not continuous on the closed interval, or we didn't have a closed interval to begin with, we didn't have both a max and a min. So I'm thinking that it has something to do with continuity and closed intervals. Now notice where the max and mins occur. Neither one of the max and mins occurred at the endpoint, did they? They all occurred at places where the derivative was what? 0. That's interesting. All right, letter E. 2 minus 3x on the closed interval. We have a closed interval. We have a function that's going to graph as a what? A straight line. Straight lines are continuous where? Everywhere. So I'm going to have another function that's continuous on a closed interval. The last 2 times that's happened, I've had both the max and the min. You think we'll have both the max and the min again? Definitely, maybe, right? Yeah. Let's graph it. The y-intercept is what? 2. And then our slope is -3. So if we go down 3, right 1, we have another point right there. There's 1. So it looks like this. Something like that. And we're going from -1 to 2. So if I highlight the region I'm looking at in green, it's going to be from here all the way to here. Just the green region. Okay. I think I can answer the question now. F has a max of what? It's at the what left endpoint? F of -1. You already plugged it in. What'd you get? You'll see here at -1, that green dot is the high point. So the function value there, if you plug it in, it's going to be 2 plus 3, right? 2 plus 3, so it's 5. And it occurs at x equals -1, which is now your left endpoint. And F has a min of what? Well, we could say it's F of 2, which when we plug it in gives us 2 minus 6 is -4. And it occurs at x equals 2, which is also an endpoint. Are there any values of x on this function where the derivative was 0? No. But yet we still had a max and a min at the endpoints because we had a, what type of interval? Closed interval. Now, if we made it an open interval from -1 to 2, would we have a max or a min? No, we would actually have neither a max nor a min. So yeah, I'm starting to really think that if a function is continuous on a closed interval, we're going to have both a max and a min. And if it's not both of those things, we could still have both a max and a min, but I don't think there's a guarantee that it's going to happen. Huh. All right, this one's interesting. F of x equals 3. This one also graphs as Rapp said a straight line. But what type of straight line? Horizontal straight line. And that's pretty significant because the other one was a slanted straight line. I know what this horizontal line looks like. And now I'm going from -2, which is going to be right about here, to 4. So now I don't want to be distracted by everything else that's going outside of that interval. So yeah, I've got a function now that's continuous on a closed interval. Every time it's happened in the past, we've had both a max and a min. I wonder if that's going to be the case this time. I wonder. Let me move this 3 up. There we go. Salvaged it. Yeah. Do we have a max? Well is right. Well is right. Oh. Oh, yeah, very good. Come back up to the definition. I'm glad you brought us here. Notice it said not just greater than, or not just less than, it says greater than or equal to. So as I mentioned down here in this note, you're not necessarily saying that it's the biggest y value to be the maximum. You're just saying that there is no other y value bigger than it, right? And to be the minimum, it doesn't have to necessarily be the lowest, but it just has to be a value such that there are none lower than it. So if we come down here and we look at this horizontal line, by definition, on the closed interval from -2 to 4, are there any other y values greater than 3 on that interval? No. Therefore, by definition, we must have a what of 3? A max. Good. F has a max of 3 for all x on the closed interval from -2 to 4. Now, I can include the endpoints, right? So notice that the maximum occurred at an endpoint, and at all the other ones on the interior, what's the value of the derivative? 0. So once again, it's occurring at either an endpoint or where the derivative is 0. That's kind of interesting, too. These are some great observations y'all are making.
Seniors, this year's prom theme will be Casino Royale. Thank you for voting. And teachers,
well,
you can place your
if f of x has a maximum of 3 for all values, then certainly, Clark, it can't have a minimum, or can it? It does. What's the minimum? Also 3. Have a good day. You're right. I wanted to make sure you got that. F also has a minimum of 3 for all x on the closed interval from -2 to 4, because by definition, there are no y values less than 3 on that interval. So the definition with the equal sign there is pretty important. Okay? Now, the horizontal lines are kind of the exceptional cases. But you just want to make sure that you're not necessarily looking for the biggest y value. You're just looking for a value of y for which there are none bigger on an interval. So yeah, we had a closed interval, and it was a continuous function, and we had both a max and a min. It's worked every time. Yes, James? If we had a vertical line, let's look at it. If I had a vertical line like this, purple. Yeah, I think you just had your question answered. That would be like x equals 3. Is that a function of x? No, it fails the vertical line test. About as badly as one can. But yeah, then you would say the maximum would be non-existent either because it's unbounded above and below. Yeah, so vertical lines are not functions. Okay, under what conditions then, down here, under what conditions do you think a function will have both, and I put a and d instead of a and, both an absolute max and an absolute min? As long as you're laughing at me and not with me, it's okay. Under what conditions will a function have both an absolute maximum and a minimum? Now, in English, would this absolute transfer over to the min? Would you transfer that by the transitive property, absolute max and absolute min? Or would you read that as an absolute max and just a min? Yeah, it's a moot point in this case because it would be implied either way. Very good. Well, I don't know. Maybe there's a theorem for that. Yes, there is. It's called the extreme value theorem, or the EVT for short. Now, this is our second of 3 very important VT theorems that we're going to look at this year. Actually, we'll see 4 of them, but 2 of them have the same name. Kind of confusing. What was the first one we had? The IVT. The I stood for intermediate value theorem. And that one just said, remember, why did the chicken cross the road? How else was it going to get to the other side? It had to cross the road, right? Because it was a continuous function. It has to pass through every point along the road from point A to point B. Okay? This one is the extreme value theorem, and it gives you the necessary conditions under which you are guaranteed, guess what? Both an absolute max and an absolute min, both of which we call extreme values. Okay? Here's what it says. If f is continuous on a closed interval, that's all we need. Wasn't it the same if part as the IVT? It was the same if part. Wow, we can make another claim. If f is continuous on a closed interval, not only does the function have to pass through all the y values between f of a and f of b on the open interval from a to b, but apparently something else we could say. Then f of x has both a maximum value and a minimum value on that closed interval, just as we've suspected, right? And notice it is on the closed interval because we leave the possibility that the extreme value itself could occur at one of the 2 what? Endpoints. So we need to make sure that we're saying that it would occur on the closed interval. There you go. So what we suspected is true. To guarantee that a function is going to have both a max and a min, we just need the function to be continuous on a closed interval. Nice. Here are some examples of functions on closed intervals where the EVT applies. From A to B, continuous on the closed interval, we have both a max at f of c and a min at f of d. Here's another one, continuous on the closed interval from A to B. We have an absolute maximum of f of c and an absolute minimum of f of b. Notice the maximum occurs again where the derivative is what? 0, and the right endpoint becomes the location of the min. And then here's one like sine of x. Now, looking at this, I should probably add another example, just kind of thinking for the future where we'll spend most of our time. What if I have something that looks like let's do pink, like this? And we'll call this C. This one has an absolute maximum of what? F of A, right? It's continuous on the closed interval. And it has an absolute minimum at what? F of C. What's the value of the derivative at C? It's D and E, right? It's D and E. So not just where the derivative is equal to 0, those are the horizontal tangent lines, but if it's continuous and the derivative's not, that's also another potential place. Now, it could have been, if the derivative is undefined but the function isn't, it could be a vertical tangent. But if it's a cusp or something like that, that's also another possible location for an absolute max or an absolute min. So we're going to want to find those. Okay. Now, is it possible for the EVT to not apply and yet still have both the max and the min? Yes. In fact, if you look at this first example here, if you make this open and that open, does that change the fact that we have both the max and the min? No, but would the EVT apply? No. So the EVT doesn't preclude it from happening. It just says if it's continuous on a closed interval, there is a 100% surefire money back what? Guarantee that it's going to exist. Guarantee. All right, example 3. Determine if the EVT applies for each of the following functions on the closed interval from 0 to 2. If it does, find the extrema. If not, explicitly state why, and then determine if the function still happens to have extrema. Okay. Here we go. We'll call each of these functions f of x, just for convenience. Does the EVT apply from 0 to 2? Yes or no? No. No. EVT does not apply. EVT does not apply. Why? Since f is not continuous, if we call this graph f of f, is not continuous, where? On the closed interval from 0 to 2. If you want to say it like that, that would be fine. I told you when we were doing this for the EVT, it's probably better if you say at x equals 1, which is an element of the closed interval from 0 to 2. But you wouldn't necessarily lose points if you just say, hey, it's not continuous on the closed interval, because that does speak directly to the if part of the theorem. Now, does it still have an absolute max or min? It does have an absolute min, right? It still has an absolute minimum of what? Of 0 at x equals 2. But there is no maximum, once again, because we can get infinitely close to 3. Okay. How about this one? Does the EVT apply? No. Same reason, right? If you just wanted to be very, not vague, but not as specific about it, you could just say the same thing. And instead of saying at x equals 1, you could actually say at x equals 0 and 2, or you can just say it's not continuous on the closed interval. It is continuous on the open interval, but it's not continuous at either endpoint. So does it still happen to have a max? No. Does it still happen to have a minimum, though? No. No max, no min. Thank goodness the EVT didn't guarantee it. That'd be weird. We'd want our money back. All right, how about this one? EVT apply? No. I'm just going to cheat, right? Copy and paste. No, the EVT doesn't apply. F of x is not continuous at 1. Does it still have a max? Yeah. It still has a max of, I'm just going to say f of 2. Perhaps it's 3. Do we still have a min? Yeah. We have a minimum of f of 0. Whatever it might be. 1/2, 1/3, who knows. And then finally, letter D. Does the EVT apply? No. The EVT didn't apply on any of those, because none of them were continuous on the closed interval. Do we still have a max and a min? Yeah, here we have a maximum of 3. I don't even know the x value where it occurs. Well, what's, again, the value of the derivative there? D and E. It looks like it's a sharp turn. And we have a minimum of, I don't even know what that is, but there is a minimum. We'll just point to it. There it is. There's a minimum value. And the derivative there is what? 0. So once again, EVT didn't apply, but we had both a max and a min. One of them occurring where the derivative was 0. One of them occurring where the derivative was undefined. So what we're going to pick up with tomorrow is, now that we know the necessary conditions under which we're guaranteed to have both the max and the min, at what different types of x values will they occur? Because what we're going to be doing is we're going to be working with equations and functions, and we're not going to have graphs anymore. We're going to do it entirely analytically. Great stopping point. Excellent time for the bell. Y'all have a wonderful, great day. Happy National Deviled Egg